welcome back to another episode of the Func Prog podcast. Okay, sorry, I messed it up right away. Let's do a do-over. So welcome to another episode of the Func Prog podcast with me, Christopher, and today I have with me a very special guest, Robert Smith. Welcome to the podcast, Robert.
Yeah, thank you for having me.
And thank you for coming. And yes, so Robert, why don't you introduce yourself?
Yeah, so very simple. I'm a software engineer. Professionally, I do a combination of software engineering and software engineering management. My interests kind of lean toward more scientific and mathematical applications, generally speaking, although I'm not wedded to those particular applications, but generally speaking, I'm kind of attracted to those sorts of problems.
Hmm.
I've been interested in programming for a very long time, like many of your guests, I suppose.
Mm.
Probably around 8 years old is when I kind of got into it.
Okay,
And I
you
sort
cut
of
your
got
teeth
into,
really early.
yeah, I kind of was interested in math at the same time. And so I had this interesting leapfrog between, or kind of back and forth between learning math and learning programming. I would always feel that if I learned a little bit more math, I could program a little better. And if I knew how to program a little bit better, I would have access to more,
Mm.
ability to do some computational math and so on. So
Okay, so there was some kind of like interplay there between
yeah,
this.
that's right. That's
Mm.
right. And then yeah, fast forward, I've programmed for a while, and I've just made a career out of it, I would say.
Mm. So when did you get your first programming job?
I did some basic like consulting on the internet when I was, I think, in my late teens, between 16 and 18. Now, these were very informal, like I wasn't getting as we would say in the US, like a 1099 or W-2. This is somebody like, oh, I'll pay you a little bit of money if you do this little thing.
Yeah, so
To
more of
me,
a side thing.
yeah, a little informal side thing. My first real break, so I didn't go to university. I was actually a horrible student academically. I mean, I loved learning, but in here in the US or the schools I went to, homework is a very important thing. And so I never did
Mm.
any of my homework. I'd go home and program or learn math as opposed to doing, algebra homework or something like that. So my grades were terrible, absolutely awful. And I actually, the universities I applied to, which were, you know, I wasn't applying to Harvard or MIT or anything. It's just
Mm.
local state universities here in the US. I was actually rejected from every single one of them. So I was
Oh
in a
wow.
little bit of a lull period. And I think it was around when I was 20-ish years old is when I had this breakthrough. I was looking for jobs, and there was an ad on Craigslist of all places saying they were looking for a Lisp programmer. And I'm like, I like Lisp. I've been interested in Lisp. This is kind of weird, but I'll apply to it. And long story short, I did the interview. I passed the interview and then relocated to Colorado, where I started working on my first programming job at all, which also happened to be a Lisp job.
Okay, so you really started out strong, I guess you could say.
I would say so. Now, the job was at a small little startup that's unknown and, never really went anywhere big. But yeah, I mean, just dove in headfirst into, yeah, career in programming, I would say.
Mm. So it wasn't called Via Web or anything like that.
No, 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 no. It was a company called Secure Outcomes. They were a company that built these little portable uh, fingerprint scanning systems for
Oh.
like law enforcement booking uh, applications. It had a little optical fingerprint scanner, a touch screen. It was battery powered. It could be used for emergency response. And the entire thing, top to bottom, was implemented in Lisp. The UI, the touch screen, the keyboard, the localization, the fingerprint analysis stuff, everything. I mean, it was almost like a little Lisp machine, I would say. And yeah, that was how I got into programming. It wasn't what I imagined it would be because I was thinking of more typical programming jobs, right? Like you
Yeah,
go
yeah.
work for a big company and you're doing some database backend stuff or something in Java or whatever. And yeah, this was totally
PHP.
different. Yeah, that's right.
Yeah. And sorry, what year was this? So this was a bit after like the internet, your first
Yeah,
internet like
yeah,
website jobs.
this would have been around like 2000. 2010 or so, plus or minus. So yeah, back in 2010, yeah, there was this startup, and yeah, so this was way well post-internet and everything like that.
Mm-mm. Okay, so and there were like these companies running Lisp in production. For some reason I always have this image of like that like the I don't know these kind of systems that you're describing. It feels like they were more common in the wild, like in the 80s and early 90s maybe. But they were still like committed to Lisp.
Yeah, yeah, I think in the 70s and 80s, there was definitely a big push for specialized hardware that ran these programming languages.
Mm.
Lisp being one of the big ones with Lisp machines, LMI, Symbolics, those types of companies building specialized hardware. But there are also many other efforts. I'm not familiar with all of them, but one such effort was like a machine that ran Oberon natively, for example.
Oh.
And so, yeah, there was these specialized efforts to make, these specialized machines. I think that obviously those didn't end up succeeding. The kind of general purpose commodity hardware
Mm.
eventually took over. And while I wouldn't say one startup working on a Lisp application is a renaissance of Lisp or anything, I do think it was markedly different from the style of the 70s and 80s, where this really was a bunch of commodity hardware that was now accessible.
Mm.
And I think it was another test as to whether Lisp could succeed on such hardware. I mean, I wouldn't call it an embedded system, but it has some underpowered, I don't remember what processor, some Intel Atom processor. It had
Yeah, yeah.
barely, it had RAM. It wasn't a microcontroller, but not too much. I don't remember, gigabyte or maybe 2 gigabytes.
Mm.
So it was relatively speaking constrained, not super constrained. And I think it was in a way an experiment as to whether a Lisp application could succeed on a platform that traditionally one would write Lisp on, I would say.
Because it was so well underpowered or however you
Yeah,
wanna.
underpowered. I mean, it was supposed to run on batteries. I mean, you could plug it in, of course,
Mm.
and it required custom hardware design. And usually, at least from the 2010s and on, or maybe even starting at the 2000s, whenever you thought about building custom hardware to solve a problem, the first thing you think of is probably not Lisp. You're probably going to
No.
think, I don't know, a C++ application or
Y-
something like that.
yeah, or like
Um,
C, or like something even more low level, maybe like just like hand. I mean, I guess there were still some like holdouts, still like hand rolling assembly instructions at that point.
Yeah, that's right. That's right. So,
Yeah.
so yeah, it was an interesting experiment, and in that respect, at least from a software hardware architecture standpoint, I think it actually worked relatively well. It was a single application with kind of a single unified hardware platform, and it did everything that the customers wanted it to do. Scan fingerprints, print them out on little these standardized like cards that the FBI and these police stations and so on use,
Mm.
and for all intents and purposes, I think it did a great job at what it was designed to do.
Yeah.
Now, there's
Cool.
another question about whether there's a market for these things and how you get into the law enforcement market and so on. That's a business question. And I don't think that the market was as large as imagined, but technologically, I think it was quite a gem, I would say.
Mm. So if you want to have a job programming Lisp, maybe you should look into like what the law enforcement is.
Yeah.
Yeah. Yeah.
Unfortunately, the company doesn't exist anymore. The CEO passed away some years ago,
Oh.
and even while he was still CEO of the company, the company was on thin ice for a long time. I think he's putting a lot of personal capital into it.
Mm.
The company is also being run from a city called Evergreen, Colorado, which is like in the middle of nowhere, Colorado. It's like 40 minutes west of Denver. And so anytime you had to go to a customer, you have to, drive an hour to the airport, spend time in the airport,
Oh.
fly to
Yeah.
whatever part of the country. And, I just think there were a plethora of other issues that didn't allow the company to really succeed,
Mm.
to my knowledge. Yeah.
Yeah. So, but like I guess Lisp wasn't really detrimental or like a key to the success of the company either. I guess.
Yeah, no, I mean, I think the like rapid development capabilities of Lisp actually allowed us to start making our first revenue very early because I mean
Mm.
the system had a lot of stuff. Like I said, it had encryption, fingerprint scanning. We had to print on these fingerprint cards with these precision because if you're printing forensic data, there's a lot of standards you have to pass to. So, one of my memories of working at this company is actually going to one of these bureaus where we validate the system so that it can kind of get the stamp of approval to be used for forensic and law enforcement purposes. And we were going through the test of scanning and printing fingerprints on these
Mm.
cards. And something wasn't quite right. It wasn't passing validation. I don't remember what the specific issue was. I don't know. It was not aligned or the it was like rescaling the fingerprint, and so the resolution was a little bit off. And what we could do is like I was there with a fellow programmer. We'd have the system running live on this hardware, and we had a REPL on it. And so while we were trying to, fix the system because we didn't want to leave without getting the system validated,
Yeah, because you had
uh,
been traveling all the way there, and yeah.
yeah, and it's like takes a lot of effort to get into these places where you have some authority giving the stamp of approval. And the last thing you want is a rejection, go back home, re-engineer whatever, and then come all the way back and reattempt it. So they were the hosts were very gracious and said it's not working quite. It's like mostly there, but these things need to be adjusted.
Mm.
So, the decision we made at the time was we're just going to try to fix it right here.
Mm.
And how do you do that in Lisp? Well, typically, you get a certain build of your software that allows you to run a REPL. And that's what we did. We got a REPL running, and like we would print the card, and we would look at how it printed, and was it right, and do we need to shift it over, up, around, according to what this what the authority was asking for, and we would just like REPL debug it until we got it right, and they're like thumbs up, good, and then we transferred that back into the code.
Oh, that's really yeah.
Yeah,
That's
it was.
another cool Lisp like REPL debugging story, I guess.
Yeah, that's right. Now, I do think this REPL debugging story is a little bit different than many that you hear historically. So, maybe we'll get into this later, but like one thing I don't think Lisp programs should ship by default is a REPL.
Mm.
I think that it's reasonable in today's day and age to like have debug builds and so on. I think that personally having everything be live debuggable where you can connect to anything and run arbitrary code is probably not the best solution today.
Mm.
But the ability to do that when you can swap out the software for a debug build or something, it's of course invaluable.
Yeah, yeah. And I mean, there's this famous anecdote, like, I mean, now I wish I had, this, like, assistant, like, I could just tell, like, Jamie, pull that up, like, but are you familiar with that incident where there was some, like, bug in the uh,
Like the
telemetry or
space
something?
probe or something.
Yeah, for the
Yeah.
space probe, I think it was the Challenger or something maybe, and there was they managed to hook up a REPL to it, and they could like actually fix the problem, so they
Yeah.
didn't have to like sort of scrap the entire program.
Yeah, I think that's definitely, yes, I've heard about it and read about it. I think that's a very interesting case. I don't personally find that to be a convincing argument that all of our applications should be architected this way. It totally makes sense that you can't go on this spacecraft, however many thousands or hundreds of thousands of miles away it is, and like swap the software. So having some ability to control it and change the software and live update it seems to make some sense. And I think it's a great story that kind of gets into the essence of REPL debugging. Unfortunately, though, I think that people took that story and inferred from it that we should now be enabling all of our Lisp applications as having REPL debugging. At least
Mm.
when I read comments and when Lisp programmers bring the story up. That's kind of the argument that's made, and I don't
Mm.
quite agree with that.
What would you say are some like cons of sort of like enabling this by default, or like having a
Yeah.
REPL?
So I think the standard is like security. If you're opening up a way to execute arbitrary code, then you will need to make some security fixtures to not allow this. Now, Lisp
Mm.
wasn't designed, in my opinion, with like all these features of Lisp, like REPLs, debuggers, were created with the idea that a developer is in control of them.
Mm.
Um, Back in the 80s and 90s, especially on like the Lisp machines, the line between developer and application user was very blurred. The thought was that that line should be blurred so that the application users had superpowers to modify the application at hand. So, for whatever purpose they had, or whatever. If you look at the old symbolics list machine advertisements for like the Genera operating system, you'll see in the marketing material, it's like you get all the source code, you can live debug it, so on and
Mm.
so forth. And that was like being advertised to people to buy the machine for application use.
Yeah.
And so the list was sort of designed with that sort of mentality in mind, and as
Mm.
such, um, I don't think people were thinking of single user workstations and whatever, not programs that are being deployed to servers where there could be remote attacks or infiltration or whatever. Um, and today I think we would broadly agree that we do have a dichotomy between developer and user.
Mm.
Generally speaking, users aren't modifying the programs they're running. Um, so having a REPL debug point, I think, is opening up to security issues. I also generally think that it just adds extra infrastructure that you don't use most of the time. Most of
Yeah.
the time, if you're deploying to a bunch of servers or to a bunch of hardware products, like in our case, if I think of a literal hardware system and there are hundreds or thousands of them out there, having remote debugging capability with the Lisp REPL specifically just isn't as valuable.
Mm.
I think that the third thing is um, even if I can debug it using a REPL, having access to the source code is immensely valuable. Most Lisp programmers are not live modifying a Lisp program solely by typing stuff in the REPL. By and large, the most popular way to do REPL development is that you have your source files, you're modifying your source files, and then you kind of send those changes to the REPL. Then, of
Mm.
course, you go in the REPL and you do a couple little experiments and you call your functions and see that it gives the right results, and maybe you make a unit test out of that or something. But there's really a conversation between your source code and the REPL.
Mm.
So I think this is the third argument sort of against shipping REPLs is that while it might give you great introspection, debug and might give you good view into system state, ultimately to make the fix, you have to go back to the source code, obviously, and that's not going to be resident on these systems as it was back in the 80s on the list machines.
Mm. Yeah. 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 The I mean, and just for those who are not in the know, like, I mean, what is a uh, what is a REPL? And I mean, and let's take it from like the Lisp perspective, because some people might have like, I don't know, the REPL has a special place in like the heart of the Lisp programmer, right?
Yes, that's right. So the REPL originally stood for and continues to stand for read, eval, print, loop. So there were four operators, or there are four operators in Common Lisp. Those four operators are the read function, the eval function, the print function, and the loop macro or special form or whatever you want to call it. These are things that are built into Lisp. These are operators that are built in. They all have familiar names. Like, for example, both you and I have heard since the dawn of programming what a print function does. But they
Mm.
have slightly different meaning in Lisp than what we'd normally expect. So Read in Lisp is a way to take input, usually from a character stream, whether that's a file or terminal input or whatever, and parse an expression into a Lisp data structure. So read isn't just read a string. It's not getting character data from one stream and putting it into a string. It's actually read character data and construct Lisp data structures, which are these S
Mm.
expressions. Um, and these are, usually made up of lists and symbols. Some people think it's an AST, but it's not. It's just lists and symbols. So the read function takes a character stream, produces lists and symbols, which usually will represent Lisp code or something of that nature. Eval will take that list data structure, not a string, and produce the evaluated result of interpreting that data structure as a Lisp program. So it'll take a Lisp program, it'll run it, it's an expression, and it produces an answer. Print is sort of the diametric opposite of read. It takes a Lisp data structure and, if you want to think of it this way, serializes it back to a character stream. And then loop, of course, will run whatever
Mm.
expression is within the loop over and over. So the whole chain looks like this: read characters from a data stream, produce a Lisp object, evaluate that Lisp object to another Lisp object, serialize that Lisp object back to whatever output stream, in loop. That is sort of a fundamental skeleton that began this whole idea that Lisp programs are interactive in some way. I can go and write Lisp code in a REPL, and it will, do whatever I'm asking, and it'll give answers.
Mm. I
Now that
think
I
yeah, sorry.
go ahead.
I think you touched on something quite interesting there as well, like in the print step when you said that, I mean, it doesn't just like, print any string. It sort of feeds you back another like Lisp form, right?
Print is a way to kind of take a Lisp data structure and produce a serialized representation of it. So
Mm.
maybe an equivalent like in Python would be the repr method. The role of repr isn't to just print something out. It's not to pretty print something. It's to create a printed representation that I could later deserialize again back into the representation of my program. That's the role of print in Lisp.
Mm.
It really should be thought of as a serialization primitive. It serializes a Lisp data structure to something that can be output to text files, be represented as bytes or whatever.
Mm.
And that's very different than, again, our normal conception of what printing means, which is to, like, I don't know, construct a string
Yeah.
and output it to the terminal or something like that.
Yeah, because I think this, like, this might sound like kind of like a surface level distinction, but if you think about it, it's actually like quite important, because if you think about how print works in JavaScript, for example, like, or like, I mean, it's not called print, but whenever you try to convert like a data structure to a string, it sort
Mhm.
of does kind of that, but like really, best effort thing, like. If you try to, or in Java, for example, if you try to, or Python, if you try to like turn an object into a string, for example, you just get like a pointer ID or something.
Yeah, and
And
I think there's another even deeper level of this, which is the whole, like, what objects are even representing with
mm.
these data structures? Well, we're representing Lisp source code in a way, not quite an AST. Eval might internally make an AST and evaluate it, but we're representing Lisp source code as objects. So it's also not just merely a way to serialize an object. It's your interface with the fundamental representation of your program as far as the Lisp evaluator is concerned. And this opens up, all this discussion about metaprogramming.
Mm.
This leads to, like, where do macros come from, all of that stuff.
Mm.
Um, but anyway, sort of this is the fundamental kernel of what a REPL is and where it came from. But then in practice, that's a very academic sort of definition of it now. In practice, it ballooned into this whole framework for interactively developing your program. So a REPL it's good and great, you can interact with it, but nowadays, and well, not even nowadays, I mean, for the past 30, 40, 50 years or whatever, the REPL has been sort of your ultimate window or gateway into the state of your program. And as such, in a Common Lisp REPL, I mean, you can do more than just evaluate expressions. You can disassemble any arbitrary function and look at the disassembly. You can profile your functions and look at how the sampling profile, like where in the assembly code the sampling profiler was spending time. You can inspect objects. You can run the debugger. You can. It's really this full featured um, development tool that lets you interact with your program in a very close way. Now, that maybe seems like a good idea as like a debugger, but what about for development? Well, as I said earlier, when I'm developing a program, you kind of think of it as like loading the stuff in the REPL. I load my program into the REPL, and then I go change some functions in my source code, and I sort of send those changes to the REPL so that I can immediately test it, use it, look at the result, or what have you. So the sort of kernel of this interactive command prompt ballooned into this much larger interactive programming tool, I would
Mm.
say. And I think that's what a lot of these other things, which are also called REPLs and like Haskell and Python and so on, they didn't really get to that point of having sort of this full featured functionality. I would say the REPL is more like an add-on thing to kind of do a couple little tests or try something out,
Mm.
not to be a very fundamental tool to the construction of the program itself in
Mm.
general. At least what I observe when people use these tools, I don't see that happening
Yeah,
as
no,
much.
I think that's completely correct, and I think maybe like a better analog is like uh, it feels like sort of in a completely like in a land far away, like we've sort of rediscovered this principle in like the programming notebooks.
Yes, that's right.
To me that's sort of the closest analog. It's like it's not only like you said a place where you can sort of I don't know, just try something out to check if a function works the way it should or something. Like it's more like a workbench, sort of, where the
A workbench, and also a place where you can actually like write source code. Like a notebook isn't just, a bunch of little tests that you write. It actually contains the source code of the things you're running.
mm,
Now, of course, as a Lisp programmer, I'm going to say the notebook is not the right place to be storing your Lisp code. And anybody who's had to like commit a Jupyter notebook to Git or something
yeah,
knows how awful it is. So maybe it's not like it's like kind of like the right idea with wrong execution in the context of like constructing a program that we want to develop as ordinary software engineers. But yeah,
mm,
I think that's a rediscovery of some of the aspects of kind of the role of the Lisp REPL, which is to collaborate with your development of the program.
mm. Yeah, I mean, because you get this reaction sometimes when people say like, "Oh, wow, REPL. I mean, big deal. Python has a REPL as well." But you're sort of selling if that's the way you think about it, you're sort of selling the idea short. So I think that it's more like, I mean, if you haven't used Lisp before, I think it's more correct to think of it, yeah, more like as kind of like a notebook thing, and not like your typical like I don't know Python or JavaScript.
This does
Uh,
sort of imply, though, a negative of Lisp, which I think has hampered its adoption practically.
okay.
Which we're talking about this great way of interactively developing the program. Like I just told you, I can profile, I can run the debugger interactively, I can disassemble, I can run whatever function. If my program is running, let's say I have some threads running, maybe I have like a game loop or something that's running, and I also have my REPL, I can, I don't know, change the size of my character on the screen or change the sprite that's loaded. I can do all of that
Mm,
interactively. And that all sounds great and amazing on paper. And it really is great and amazing. But what that means now is the tool that we use to develop Lisp must now be enabled to work in this fashion. And so we've had things like VS Code or Atom or back in the day Sublime and whatever, which first and foremost started as like text editors
Mm.
because that's how most people develop code. You find a
Mm.
nice text editor or an IDE, you write all your code and you have some buttons there to compile your project or whatever. And those things don't sort of speak the protocol, not literal computer protocol, but the bigger picture protocol of developing a Lisp program. And so, what happens when you tell somebody, "Hey, go try out Lisp, try this amazing REPL experience"? Well, now I have to tell you, okay, go download Emacs, go download Slime,
Mm.
go download SBCL, go down and run all these things. And it's like it's so much work to get started to even try this new paradigm. People have tried to put this stuff in like VS Code. There's an extension to VS Code called Alive. I don't have the most up-to-date knowledge on the latest developments, but last time I tried to use Alive, every REPL request I would send, it like spawned a new thread to run that request and then report the result. And so if you're like doing a lot of things, or maybe the request you sent didn't terminate, you just have this thread running in the background, and then it'd be slow, and then there would be, I don't know, all these issues came up with it. And so it didn't really turn into like a Cadillac experience. Maybe
Mm.
things have changed since then, but the sort of best in class experience with modern day technology, short of picking up an old Lisp machine, is to use Emacs and Slime for Common
Mm.
Lisp at least. And I think that's a very large impediment to, I don't even want to say adoption, but even just trying it. I mean, it's the weekend right now. It's Sunday. Here in
Mm.
California, it's a little past noon. I have, a portion of the rest of my day to try something. Is the best use of my time this day just for fun to go try to figure out a new text editor, a new paradigm of programming with a new language? It's just kind of a lot to ask for, I think.
Mm. Yeah, yeah.
Um, and so, one of my big interests has been, somehow to improve the situation. But I also want to be a programmer using it. I
Yeah.
don't, I personally don't have a lot of interest spending my time to build the infrastructure to make it easier for others. And I think that's true among a bunch of Lispers. They learn how to use Emacs, they learn how to use Slime, and they just run with it and use it. And then they go tell everybody on the internet how great it is, hoping to, catch another person or whatever.
Yeah, yeah. Like, keep proselytizing
Yeah,
the
right. Yeah, that's right.
Emacs experience.
Yeah, that's
Uh,
right. That's right.
but have you seen the Calva for closure?
Yes, yes. This is something that I've been very jealous of the Clojure community on, which is historically they've been very good, I think, at developing IDE technology for Clojure to do, take advantage of the things that we do in Lisp more broadly.
Mm.
For whatever reason, possibly due to tooling, possibly due to ideology, whatever reason, Clojure ecosystem, community, programmers, everybody have focused on these issues of making really nice tools. Even in Emacs, they have a nice tool. I remember way back in the day, I don't even know if the project is still active or not. I'm not sort of connected to it. But Light Table was a
Mm.
huge
Yeah,
thing when
yeah.
it came out. It's this, it looks fresh and cool and interesting. And it's sort of a one-stop shop for at the time writing Clojure code. And again, when you kind of compare it to situation in Common Lisp where you have to use this old crusty editor, which I love, by the way. I love using Emacs to be clear, but it's an old crusty editor with this weird thing called Slime that has a web page that looks like it's from 1992 or something. And a separate compiler that when you run this compiler, you get the worst terminal experience ever. Like you can't like move your arrow key left and right and stuff like that. It's just night and day different. So I've been very impressed with what the Clojure community has done to make programming in their language easier, and it's paying dividends. When you hear about Lisp these days, more often than not, you hear it through Clojure.
Mm.
I think.
Yeah, yeah, yeah. I think it's like, it's there's always been this thing with like, the And I guess this is the case with like every technology that's a bit cutting edge. That you have like you have a bunch of early adopters who are very like they take to new technology very quickly, and like they're really hungry for knowledge, and they don't really mind you know if Emacs, like they might see getting like Emacs up and running as a fun challenge, like whereas you have the other camp who's more like they're more interested in getting things done, like okay, what can this tool sort of do for me, like what can I build with this tool that I couldn't otherwise. And like if like you said, if it what it takes is to sort of like learn a new, well, install a weird editor that you haven't used before, and then like a bunch of extensions, and to learn a whole new programming paradigm, they might just like, yeah, no, I think I'm gonna stick to like JavaScript or whatever.
It's funny you bring this up. I was just thinking about this because I got a piece of feedback or bug report or something on the Colton project, and the feedback was basically like, please make it a lot easier to install, or something like that. And I was thinking, back in my day, when I was experimenting with programming languages and stuff, you know, uh, I'm talking, I don't know, maybe from the early 2000s. A lot of times, if you wanted to use, for example, like standard ML,
Mm,
cool language, a lot of, there's a lot of academic backing. It's kind of, there's legitimacy around it. It's not some hobby project.
yeah.
It's a very serious project. If you wanted to go run standard ML, first you found some web page that had a compiler like SMLNJ or Milton or whatever, and you would download like a tarball. It would have a binary that only ran on some particular flavor of Linux, on one particular flavor of processor. Uh, it came with maybe some bash scripts to like run it or something like that. You run it and has no other features included in it except for like just a REPL, maybe a .el file for Emacs integration. And like that's all you had to start using this new programming language. Now, back in the day when I would do a lot of language experimentation, like you said, that stuff was super exciting to me. I didn't care that it was like this horrible process to get it up and running, and that it was kludgy and hacky and whatever. It was just, it felt like magic to see a new language, like especially a functional language like standard ML at the time, be able to do something in my terminal. And
Mm.
I'm just comparing it to today, where like Colton, for example, uh, you git clone a repository and you type ql quick load Colton, and what comes with that is the entire Colton distribution, a package manager which will load whatever you want in Lisp. It's natively integrated to Emacs, although Emacs isn't required. And I'm thinking like the difference in like what is being offered between today and even 20 years ago is vast. And I feel, I mean, I don't, it's not like I sampled the population back in early 2000. Maybe people were also complaining to the standard ML guys that installation is also difficult. I'm not sure. Maybe I was just of that camp that you described. I was just excited by the challenge, and I felt like I was discovering something new that nobody else knew about or something. But I think it's an interesting observation. It's led to some interesting difficulties in what to prioritize when
Mm.
building a new programming language like Colton.
Yeah, yeah. I mean, it's always like onboarding is like, I don't know, feels difficult, and it feels like the bar, uh, the like you said, like the bar was low before,
Yes, very
and
low.
now
Yes.
it feels like it's almost incredibly high because people have very high expectations of a programming
Well, these
language.
days, I almost feel like you need, a fancy website with a big hero image and, some big text, in the hero image saying, reinvent programming now. And you scroll,
Mm.
and I don't know, it shows you all the features of the language, and there's, you know, perfect documentation and so on. I mean, the bar, I think, really has increased in terms of, um, making a project feel like a legitimate project that's not just for kind of weekend hackers, I would say.
Mm.
Is that a good
Yeah.
thing or bad thing? I'm not sure. It just means that the barrier to entry to introducing new technology, or programming language technology specifically, I think has just increased. I
Mm.
mean, if you go to like the Reddit programming languages subreddit, you see people are making new languages all the time, and most of them aren't used by anybody. Uh, I mean, one, because the audience is just not very large, but number two, in my opinion, I think it's because they just don't really, they look like weekend projects. Most of them are weekend projects, and they are only attractive to people who similarly want to experiment with, weekend projecty type things.
Mm.
So yeah, but the bar has definitely been risen for really making legitimate programming technology, I think,
Mm.
or advertising it and all that.
Yeah. 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 And maybe this is a good time to, or I don't know, maybe we should cover real quick, like, what Common Lisp is. I mean,
Yeah.
of course, you can hear by the name that it's a Lisp, but there are a bunch of Lisps out there, like, Closure, Scheme, and but what makes Common Lisp stand out from those in
Yeah.
your mind?
Yeah. So there's a whole history of Common Lisp. I'm no Lisp historian, so I'm going to spare the embarrassment of giving a bunch of wrong information. So I'm just going to kind of cut to the chase about, to me, kind of what Lisp offers and kind of what it's all about.
Mm.
So Lisp was designed to be an industrial language. It was designed to be something to solve quote unquote real problems from actual industrial use. And so it was co-designed by a bunch of industry members and whatever. So when you actually open up Common Lisp, you do see a lot of features that you would expect to have in a sort of production language. Debuggers, profilers, steppers, um, an object system, so you can write modular programs, all of that stuff. So I guess my first point is the sort of ethos of Lisp was to be an industrial language. And you see this plainly when you first look into, well, how do I use Common Lisp? Well, you need to download a compiler. Well, there are lots of different compilers because it's a standardized language.
Mm.
Most of these compilers are very robust, have been in development for a long time. And maybe interestingly, you'll find that there are commercial compilers available. You can
Oh
get a
yeah.
you can get a Common Lisp compiler by Franz called Allegro CL. You can get a compiler called Lispworks by a company of the same name, Lispworks. And so already you kind of feel that this is an industrial language. Um, Lisp, Common Lisp specifically, kind of the features it offers is like the ability to write multi-paradigm programs. I mean, it really has good support for imperative programming, surprisingly.
Mm.
It allows you to mutate stuff. It allows you to make arrays and modify it. It has goto built in the language. Like there's an operator that allows you to do like classic goto, like go to this label and jump around.
Yeah, it's like
Um,
basic all over again. Like,
yeah, right. So like it has true imperative features. It has true object orientation features. This whole people call it different things, close, class, CLOS,
yeah, Silas.
the Common Lisp object system, and it's this like very baroque, interesting system for doing object-oriented programming. Classes are different than methods, so classes don't own methods like in a typical Java or C++
Mm.
style of object orientation. Um, you can methods themselves can dispatch on multiple arguments of the argument
Oh
list,
yeah,
not
that's
just
right.
one that it operates on. Um, and so it's this and then the whole object system itself is like programmable in various ways. So you have this amazing object orientation system. And then it's also functional, like built into the language. Obviously there are first class lexical closures. There are higher order functions built into language for various things, like your mappers and your reducers and stuff like that. Um, and then, the venerable macro facility. So it's like also a meta programmable language. So my point here, I think, is that Lisp was designed to be industrial strength, so it comes with a lot of tools that you expect to build actual programs that solve customer problems or whatever.
Mm.
And then in addition, it gives you a lot of directions on how you wish to architect your program. Whether it's, it doesn't force you into a single dogmatic way of reading and or writing programs. It kind of gives you this multi-paradigm thing.
Yeah, I mean, it
Um,
feels very pragmatic. Like, I mean, if you compare to something like Scheme, or which is more like, I mean, strictly functional. I mean,
Yeah, it's one of these languages that I think, like in its original design, I think they really tried to make it batteries included. Now, I think there's a lot of criticism we could give today about whether, like, how good are the have the batteries stood up to the test of time. Somewhat. The standard library that's built into Common Lisp is maybe a little bit it's lacking in certain areas. So, for example, something that most people see as standard in modern languages is the ability to create a dictionary or a map very easily.
mm,
In Common Lisp, if you want to make a map, which is called a hash table in Common Lisp, you have to call a function called make hash table, and it creates an empty table. Then you have to do set f get hash blah, and if you want to populate a dictionary with, I don't know, 10 items or something, you have to write 10 lines of code to build this. Now, a Lisp programmer will tell you, hey, you don't need to do that. You can write a macro that
mm,
will
just
make it
write the
easier. But
macro.
like most people expect that you shouldn't have to write a macro for something that we today see as kind of a basic piece of functionality. But
Mm,
with that said, dated aspects of the language notwithstanding, it's definitely designed to be a pragmatic language. It trades some what I might call academic elegance for practical utility in certain areas. And largely, I think, while I wouldn't agree with all the design decisions that exist in the lens of 2025, I do think it succeeds at being a pragmatic language.
mm. Yeah, and like you touched briefly on the macro system, and it feels like that's one more area where it's like very pragmatic, because as far as I understand, I mean, macros in Common Lisp are less limited and more powerful compared to those in Scheme, for example, like the
I would
standard
say
Scheme.
I don't like to think of it in terms of whether it's more or less powerful. I would say whether it's like lower, higher level. So the
Mm,
macro system in Common Lisp is very low level. A macro effectively, we were talking about earlier the whole read function and print function, how when we read a Lisp data structure that represents source code, and print will reserialize that back to the stream. So this idea that a data structure represents code is like a key part of Lisp. In a macro, all it is in Common Lisp is just a function that that modifies or that transforms rather a one of these data structures representing Lisp code. In fact, it's by the standard. I don't remember the exact verbiage in the Common Lisp standard, but it's actually supposed to be a pure function. It is
okay,
not supposed
yeah.
to actually do any mutation or anything. It's supposed to be a pure function such that if you give the same data structure representing source code as input, you should always get the same source code as output, because the standard doesn't define when macros are going to be invoked and what order they're going to be invoked. So they should be pure functions. But yeah, the macro in Common Lisp is really just a like source code transformer. It just takes code as input, runs arbitrary code that you want to modify it, produces code as output. Scheme programmer or the Scheme language and other macro systems try to be more sophisticated than that. They try to say, okay, well, XYZ mistakes can be made with such a low level macro. You hear about this name capture stuff. You might make a macro that expands into code, but that code that it expands into might inadvertently capture some name of the surrounding code and context.
Mm,
So, the details don't matter. The suffice is to say that, you can run into these sort of bugs or issues, which common Lisp programmers have designed sort of patterns around solving. But Scheme programmers say, look, we don't want these types of issues to happen. We are going to build a macro system that fundamentally disallows it. We're going to make it so that you have to write macros in a certain way to do a certain kind of transformation. And the benefit is that these issues won't happen. The negative is that now you have a less flexible abstraction. Now, for scheme programmers listening, of course, there have been multiple evolutions of the scheme macro system. There's an array of options practically when you download a scheme implementation, or if you use it, the close cousin of scheme, Racket. Racket has
Mm.
a very sophisticated macro system. So I don't want to say that scheme programs can't do what Common Lisp does. I would say the normal pattern of usage is of a different sort of mentality to use a higher level feature preferentially over lower level. But Common Lisp is just like very like it gives you the tool. It can do mostly anything, but it has sharp edges if you kind of don't know what you're
Mm.
doing.
Yeah. And I guess this sort of segues nicely into Colton, because Colton is in itself implemented in Common Lisp, but maybe I'm getting ahead of myself. What is Colton?
Yeah, so Colton is a language embedded in Common Lisp that allows you to write strictly typed functional programs in a style similar to your OCaml or standard ML, maybe to some extent Haskell or Rust. So it is a strictly typed functional programming language embedded in Common Lisp. It's interoperable with Common Lisp, meaning you can call Lisp from functions from Colton, you can call Colton functions from Lisp without any overhead because it's embedded in it. It's not like a separate thing with a foreign function interface. And then lastly, I think the big thing is that it takes the type system of Haskell and makes it available to Lisp programmers via Colton. So I think that's interesting because typically the Haskell style type system has just been in Haskell. Languages like Rust, of course, have notions of like traits and stuff like that now, but your standard MLs and OCamls use a completely different mechanism for this kind of polymorphism and what have you. In Colton, we have type classes and the like. So it is a language that sits within Common Lisp that allows you to write strictly type functional programming. I like to call it algebraic programming. I don't know if that's really a good standard term, but when I talk to some people in my professional life, like, hey, we have strict types now. They're like, oh, well, we have that in C++ over here. And I'm like, no, it's not that kind of type system. It's the type system of the ML descent, which I usually call like algebraic types, although I don't think that's like a good official term.
Mm. Okay, so you sort of retrofitted a type system onto Common Lisp, which is like a dynamically typed.
Yeah,
Uh,
I wouldn't say so when I think of something like TypeScript, I think of retrofitting a type system onto an existing language.
mm.
Colton, I would say, is more we introduced a language very similar to Lisp. Actually, it's very close to Scheme within Common Lisp, such that within that language, you have static types. There was a lot of thinking very early on whether a powerful type system could be retrofit onto Common Lisp, and my answer to that was no. It's not. Lisp is too flexible, too dynamic, too. I mean, I just told you you can use GoTo and stuff like
Mm.
that, and now you're going to try to put like a Haskell-like type system on this. I didn't see, and an object system that allows arbitrary and multiple inheritance and dynamic dispatch of multiple arguments. I just saw it as not feasible to truly have the same Common Lisp language, but with the rigor of types. So
Mm.
instead, within Common Lisp, you can almost think of it as a sub-language that allows most of the things you can do in ordinary Lisp code, but are sort of locked down to be able to be typed by a sophisticated type system.
Mm. So, but yeah, and you still have full operability with Common Lisp, if I
Yeah, yeah,
understand correctly.
you can weave the two together. You can write them side by side. They can call each other. Colton code is just embedded in your Lisp project, actually is just an ordinary Lisp file. So it's not like a separate tool chain or anything like that. You load the code the same way that you load any ordinary Lisp code.
Mm.
The same tool chain, the same build steps, the same build system, the same compiler, the same, all of it is the same. And Colton code is basically compiled to Common Lisp. So it turns into Common Lisp code as well. So it makes interop between the two languages extremely easy. But it is, in a way, its own separate language. It has its own syntax, and it has its own very similar but slightly different semantics.
Mm. One thing that I saw your presentation about Colton that you shared, and we can link to it. It's on YouTube. But one thing that impressed me was the fact that it seems like you get pretty good type errors and stuff. Like when you compile your Colton code, it looks like it can sort of highlight the line where the type checking failed, for example.
Yeah, this was very important early on. So usually when you write a DSL in Lisp, a domain-specific language, almost always you're writing that DSL from the perspective of, manipulating S expressions, I guess you would say. And so when you actually use this DSL that you've built in Lisp, oftentimes the error messages are atrocious because you never cared about it. You didn't parse it, you didn't track line or column information, you didn't do any of that because in Lisp it's so easy to just write things like macros to manipulate code without having to care about any of this extra nice stuff. Colton, we paid a lot of attention to making sure that we do things like track line and column information so that when errors are issued, you get something that is very familiar to, let me say, the modern day programmer. We want to see errors come out and print the chunk of source code and highlight with an underline and give suggestions. A lot of a lot of this design was taken sort of from the Rust playbook, I would say.
Mm.
GCC and Clang were also sort of influences. I think GCC kind of followed Clang with their error messages a little bit. I don't know the history of it. But programming tooling definitely has moved in a positive direction of making errors more understandable, and Colton takes that extremely seriously.
Mm. Because yeah, that's usually like one of my big like one thing that sort of makes me a bit wary of like DSLs is the exact thing you said, like the fact that like usually when you have people say like, oh, you can program in the language of of the domain, etc., etc., which sounds great on paper, but like then usually in practice it's like, yeah, I get a very specific language, which is good, but the language is kind of crap, which is,
Yeah, right, right.
but
This
it
is
mm,
this is a very, very it's a subject that I have a lot of feelings about, I'll say. I'm through and through a Lisp programmer. I have been a part of the Lisp community, whatever that is, for a long time, and I also get to listen to other people arguing in favor of Lisp. And indeed, exactly as you say, one of the big headline features is that you can build your own DSLs, and the DSL is going to match the domain exactly, and it's going to solve problems succinctly and whatever. But then you look at example DSLs and you make a little typo or error, and it's the most inscrutable, macro expanded, whatever thing that you is impossible to understand. Now, but nonetheless, we achieve relatively good error messages with Colton. So, like, what is the root issue here? I think that historically, there have been many books written about Common Lisp, like The Great Paradigms of Artificial Intelligence Programming by Peter Norvig, the books by Paul Graham, such as On Lisp, or The Practical Common Lisp is another great book. The thing about a book is you have to make your examples reasonably concise to fit in a book. Generally speaking, books don't have a fully engineered program to the standard that we might expect in professional software engineering. It's a
mm,
book. It's supposed to teach you how to do something,
yeah.
obviously. Most of the time, macros are introduced in these books, and the example macros that are shown are, simple things like, anaphoric if operators and, whatever other things that people cook up that you can implement in 5 or 6 lines of Common Lisp.
Mm.
The thing is, though, and I think this is underappreciated, is that writing a very good DSL using macros is just hard work. The thing with the Common Lisp is it's very easy to hack something up and make something that'll work, in the good case. But to make it work from the sort of the perspective of user experience, you know, yes, I'm writing the DSL and you are going to use it, that takes an enormous amount of extra work. It takes a lot of time to write all these extra error cases, to detect these error cases. In the case of Colton, to track line and column information and all of that. And so, kind of my conclusion from all of this is DSLs are great, but in order to really ship a DSL, as it were, you need to really put in the effort to make it a good DSL, not just in terms of its syntax and semantics and whatever, but also the experience using it. Error messages should be phenomenal. Documentation should be phenomenal. Examples should be provided and so on. And I think a lot of people just don't want to do that work or see that work as redundant or what have you, because it does make the code less elegant. I mean, adding all this extra stuff makes, what was originally a 5 line macro into a 50 line one, for
Mm.
example. And it's just extra work that I think a lot of Lisp programmers maybe feel a little bit allergic to because they just don't see it as a necessity. If you use it correctly, you won't run into any problems. So I'm a big fan of DSLs, but there's a huge cost to building them and making them very good, I
Mm.
think.
Yeah, it's kind of like you said earlier about the programming languages, Reddit, for example, where you have all these people who like they share their programming languages, and there are probably about as many programming languages in that subreddit as there are users, and probably the amount of users per programming language. This programming language approaches one pretty much at the limit. And I guess it's sort of the same mechanism, like building a language. That's just like the first step. It's like the first step on a long journey of actually making something usable. Because just like you said, you need you need good error messages, you need good documentation, you need examples, you need it needs to be ergonomic, like all these things. And yeah, maybe like you said, when you come up with the idea for a DSL, maybe you're not really taking that whole like total cost of ownership into account,
Yeah,
maybe.
yeah, I completely agree. I think that writing a DSL, especially if you're writing a DSL with Lisp and macros and whatever, but it doesn't matter if it's Lisp or not. A DSL is not like a get out of jail free card for making a bad user experience. Like if you want a DSL really is an exercise in language design, in language implementation, and I think it should be done, broadly speaking, with the same rigor as you would if you were just making a standalone language. The fact it's a DSL gives you a lot of things for free, and you ought to take advantage of those things for free, such as the compiler in which the DSL is being implemented, like the Lisp compiler, for example. You don't have to care about making sure your DSL compiles the native code. You get that for free.
Mm.
You should take advantage of those things, of course, but that's sort of the back end of the language. What the user interacts with and experiences is also important if the goal is to make the DSL a functional part of a code base that you intend other people to use. Now, again, if you're writing your own little personal weekend project and you're experimenting with new syntax for this great object system that you want to build, and you want to build a little DSL for, I don't know, message passing, whatever, or you want to build a, I don't know, Erlang style concurrency layer to Lisp, and you're just playing around, of course, like any program, you can skip writing your documentation, you can skip making it reasonably good. But if you're going to write this code in the context of an organization, or I don't know, you're building something with colleagues, or you want to make an open source product or something like that, where you really want other people to use it, I think you're you will give DSLs a bad rap if you're not putting in that extra effort. And I
Mm.
think that's been a historically an issue with a lot of DSLs that have been published using Lisp.
Yeah, because like I guess it's easy to underestimate like the complexity of the like all of the things you need to do in order to like just not make it work, but actually make it pleasant to use and actually allow people being productive. But I wanted to ask you like about like Colton, like how come you came up with Colton? What was like what was the motivation?
Yeah, so the model of programming in Common Lisp to me is has not been surpassed by other languages. Meaning everything we talked about at the beginning, this whole REPL interaction, the interaction between your editor and the running state of your program. The fact that programs in Common Lisp are built in a very incremental and interactive fashion, for me, is like a superpower on testing the idea space and converging to some solution to whatever programming problem you're working on.
Mm.
It's absolutely invaluable. So I love that aspect. Um, the second thing is that Common Lisp in general, when I write Common Lisp code that I intend to be efficient, I kept feeling this really uncomfortable trade-off I kept having to make. So like I told you, I'm very interested in like math, in computation, in all of that. Um, a lot of things that I do computationally are just expensive. You have to go through, I don't know, millions or billions or trillions of floating point numbers in order to manufacture some answer. So when Common Lisp, renowned for its flexibility and this amazing object system and, first class lexical closures and a macro system, and all these great features, as I was writing a lot of these programs historically that deal with high performance, I felt like I was pushing against this trade-off of generality of my program, generality, concision, um, ease of understanding, and performance. When I wrote a program that worked, I remember actually a specific example. I wrote this multi-phase Rubik's Cube solver, this thing that searches a bunch of states of the Rubik's Cube and finds short solutions that are useful for solving it by hand. So this was a tool to actually find, as they call it in the Rubik's Cube community, algorithms that you can execute on a Rubik's Cube to accomplish some task, maybe move these cubes around or flip this edge or whatever. And so I wrote this program, and it was this beautiful program written in Lisp. It was very easy to read. It was very compact. It was very nice. But you'd run it and it would take like 5 minutes to find an algorithm, to find a solution to whatever Rubik's Cube problem you're giving.
Mm.
I'm like, okay, that's understandable because I didn't like declare any data types. I didn't use good data structures. I didn't, I could cache this result, do this. And so in order to take that program for taking 5 minutes to solve something to something smaller, now I have to go in and declare all my data types. Okay, that's step one. Step number two is get rid of any like dynamic dispatch. I was using CLOS for everything and generic functions and whatever. So it's like, okay, get rid of all those, turn these into structs. Okay, so I declare a bunch of types, turn it into structs, do other algorithmic optimizations, and this beautiful program turned into this like giant multi-page inscrutable thing that it was just harder to understand, modify, and edit. But it did get to the point where, the 5 minutes it took to solve something was now, something like a second or something. So
Mm.
this like multi-order of magnitude improvement of performance. And like
Yeah.
I felt for a long time pretty satisfied with that because I felt like, okay, most Lisp you can write most common Lisp you can write can sort of be the elegant, easy stuff. Because not everything is performance sensitive. A lot of stuff is just shuffling data around, representing your domain, and all of that stuff. So I was actually pretty satisfied that like most of my program I could write in kind of this nice, beautiful way, if you want to call it that. And then when I needed to, I could really dial in and make something fast.
Mm.
Not dissimilar to the philosophy of like the Python programmer, where they say, look, Python is great and good and nice, but if I really want speed, I'll rewrite it in C or something. I kind of
Yeah.
had that similar mindset in Lisp, except I didn't need external tools. I could just do it all from within Lisp.
Pretty Lisp or like fast but less pretty.
Yeah, and the fast and less pretty Lisp is basically almost looks like C code. It's very imperative. Every single array access is measured and optimized. All the types are monomorphic. It's very straight line, no nonsense, C or Fortran looking Lisp.
Mm.
Again, I
And
think it's amazing that that's even an option, to be clear.
yeah,
I think
and like I mean, Common Lisp is not a slouch either, right? Like just out of the box, even if you don't have optimizations in mind, it is pretty fast already,
Oh yeah,
right?
definitely, definitely, absolutely, yeah. No, by default, for the most part, a lot of things are pretty well optimized. So if you write your program in a reasonable, and if you're not being obtuse in the way that you write your program, yeah, you'll get reasonably good performance out of the gate. But for the types of problems that I'm interested in solving, reasonably good performance is simply not good enough. When you're
Mm.
searching trillions of states of something, the way that I always think of in my head, if you're, whatever thing you're computing or solving, there's some number of things you're looking at. In the case of Rubik's Cubes, it's looking at trillions or tens of trillions of states, and you have to think every single thing that you are doing for each of those states is multiplied by 10 trillion.
Mm.
So if I have to do a dynamic lookup of a method, that's going to happen 10 trillion times. Whatever time it takes, you have to think about moving the decimal point over 9 or 10 places, and you'll get the real timing of what happens. Um, so yeah, definitely, Common Lisp is reasonably good out the gate for programs. The compilers are reasonably good, and then if you really want the super high speed stuff, you can really kind of beat your program to a pulp and make something fast. So I was reasonably happy with that for a while. But then I kept writing these programs, and then I'm like, okay, one of the big things is this other project I was working on to compute pi to high precision. This just fun hobby project that I work on every so often. And originally, the way that all of the arithmetic is done, like this super high precision with billions of digits, arithmetic is done is using these high precision convolutions using floating point numbers to do fast multiplication. The details don't matter so much, but then I like discovered at some point along the way that we could do a better job if we change all that arithmetic to use modular arithmetic. So instead of using double floats and this advanced math, you do all of that same math, but you do it over these different number fields. Over, you do these modular arithmetic modulo some prime or something like that. Again, the details don't matter. I had my hyper optimized Lisp code that was all ready and situated for running with floating point numbers, and now I needed to change it to do modular arithmetic.
Mm.
And it's like it's it was very aggravating to me, like almost on an ideological level, that I couldn't very easily just go change it.
Yeah,
So
because now it's pulp,
what?
right?
Yeah, right. It's already pulp. Like now I have to kind of back up, figure out what the algorithm is, go do surgery on it, change it, and whatever. So okay, so what do I do? My first instinct as a Lisp programmer is, okay, I'm just going to write a macro. I'm going to write a macro such that all the individual operations that I need to do are going to be parameterized by the macro. So when I have to do addition, I'm going to provide that to the macro. If I have to do normalization of some array, I'm going to have that as a parameter of the macro so that I can write my macro, define fast pi calculator, double float times, whatever, and then define fast pi calculator, uh, uh, you know, integers mod, whatever prime, blah, 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 blah. And, it did the job. But again, it didn't feel like the right thing because now I felt like I was doing what everybody derived C++ programmers were doing, which is just like you're doing template programming at this point. I literally
Mm.
built a template of code in the macros just filling in
Yeah.
all these little blank spots. And it's like, what am I doing? This is like, it's this trade-off in Lisp that I keep running into. And then I'm like, okay, well now what if I just start doing introspection? Whatever. I'll spare you all the details of the story. And I finally said the root of the problem here is twofold. Number one, I keep wanting to have abstractions on types. I want, Common Lisp has types, sure, but they're mostly like monomorphic types. You can declare something as double float or
Mm.
integer or this or that, but it doesn't have like, for example, the map function in Common Lisp doesn't have like a notion of a type variable. It just says the map function first argument takes any arbitrary function that takes any object and returns any object. And then the second argument is believe it or not, a console. Uh, Here's a very funny fact. This is maybe
Mm.
embarrassing. I shouldn't say it, but Common Lisp doesn't actually have a true list data type.
Oh,
The
really?
list type in Common Lisp stands for an object that is either nil or a console. It doesn't have any idea of list structure in the list data type in Common Lisp. There's no recursive list type in Common Lisp because the type system is just too weak to adequately represent that sort of thing in any useful manner. There is something called a satisfies type in Common Lisp, but it's like basically allows you to put a runtime predicate. Whatever, the details don't matter. The type system of Common Lisp just isn't super good for this sort of higher level functional programming. So I'm
Yeah.
like, really what I need is a good type system. The second thing I need is to be able to compile code in a way that can take advantage of optimizations that we typically cannot do in Common Lisp. Again, Common Lisp is this very flexible language that allows redefinition of functions and classes and whatever. And so when we compile code in Common Lisp, we have to account for the fact that those things could happen, which means certain optimizations can happen. So I'm like, okay, after thinking of all that, I'm like, okay, what I really want, the type system I've loved the most in my career is Haskell's. It feels beautiful, elegant, algebraic data types, all of that stuff. Type classes, it feels very natural and very simple and very nice. So I really want that. But I also want to have something like, a compiler along the lines of like Milton, the famous standard ML compiler, which is a famous whole program optimizing compiler that produces like screaming fast code. It's like, I really wish I could take those two things and marry them together, but then I also want to continue developing Lisp code in this interactive way where I, have a conversation with my program through the REPL. And there's just nothing on the market that looked like that.
Mm.
There were things that kind of were rough approximations, but all of them were just kind of crappy and not good, in my opinion. Uh, And so that's when, one weekend I'm like, okay, how hard could this really be?
Mm.
And I like
Famous
pull up,
last words.
yeah, yeah, yeah. I pull up, the one of the original Hindley Milner papers with algorithm W, and I'm like, okay, this, the Hindley Milner type system, it's like it fits on a few pages. It's not too difficult to understand. Let me just implement that in Lisp and then wrap that type thing in a macro so that we output Lisp code but the macro will do like a type check first. And that was sort of the core beginnings of Colton, was an experiment in implementing the Hindley-Milner type system as a macro in Lisp. Um, all of this was born out of the desire that I really just want to have really fast code that is written in a way that's not like obtuse and
Mm.
ugly. Basically,
Yeah.
is kind of what it comes down
Yeah.
to.
I
And then it
think
kind
this
of
is
went off from there.
yeah, but I think this particular point is really interesting because this feels like a common, I don't know, like some kind of like it's a bit counterintuitive in a way, but it feels like the more sometimes when you raise the or when you raise the abstraction ceiling of something, you sort of get a new optimization boundary as well. Like,
Mhm.
because it feels like sort of the thing that Colton does is so you sort of restrict what can happen because
Correct.
it needs a type check. And since, like, the programmer is limited in what the programmer can do, like, that leaves the compiler to sort of kind of do what it wants. And
Yeah, yeah, that's exactly right. But and so now it's like a trade-off. Like, how much do we want to limit the programmer in order to achieve these great optimizations? Like, there's another famous compiler, scheme compiler, that's called Stalin. Stalin is it's sort of a joke. The tagline is Stalin brutally optimizes, and
mm,
it's the scheme compiler that is it's one of the craziest pieces of code. I recommend everybody go look up the Stalin compiler and look at the source code. It's like one giant file that's like 50,000 lines of code of scheme code, no documentation, no nothing. It's just straight line code, and I think it was written like largely on a train on one of these little small, I don't know, it was an EEPC or something, but this, I have no idea how the guy that he's a professor at Purdue, I believe. But
a
anyway,
long train ride.
yeah, yeah, he would write this on the train. I believe. I don't want to make up stories. I think that's the case. But anyway, this compiler is absolutely incredible. It optimizes scheme programs to be like faster than C. It like makes your scheme program not allocate anything. All the closures like become static or inlined. Um, Floating point performance is amazing, incredible. But the catch is like you like basically can't load libraries. Everything
Mm,
must be like floating point numbers. Your pro like the length of your program, like the efficiency of the compiler is like cubic in the length of your program. So if your program is at all long, it's like going to take ages to compile. But anyway, it has so many of these restrictions, but you get incredibly fast code.
mm,
Um, with Colton, it's sort of okay. We're not going that far down of building optimizations, but like we do have to introduce restrictions. But like there's this trade-off, like I said, of how many restrictions do you want to introduce at the expense of like programmer convenience. And this is where I felt like I'm not going to solve this trade-off academically. I'm not going to try to innovate on type system technology, programming language technology, whatever, in order to solve this. I'm going to be very pragmatic about it. I'm going to say, I can write the parts in Colton that I feel are relatively static, that benefit from types and optimization, whatever, and I can write the rest of the program in Lisp. And if as long as they can interoperate in a relatively easy fashion, maybe not perfectly seamless, but relatively easy, like it's easy to call a list function from Colton and so on, then I can sort of enjoy the benefits of both. So when I do go write my pi calculator, I can write all of the like command line argument processing stuff in Lisp because who really wants to do all this super strong static mega optimized stuff for like parsing a bunch of strings and user interface? Maybe some people,
mm.
not me. But the actual computational kernel part, yes, I really want that to be very rigid. I want a nice, I want the domain to be modeled with nice types. Um, and I can write that part in Colton. I can kind of switch between the two depending on how much rigor, rigor is not quite the right word, um, how much I want the language to work for me to both check and optimize the code, I would
Mm.
say.
Yeah, yeah, yeah. I think that gives you a really good overview of, like, the motivation. But I mean, did you find any other benefits to, like, introducing static typing other than performance? Like, I don't know, did it make the code easier to
Yeah, yeah.
and in the large, like, in a larger collaborative setting, for example?
Yeah, there are two big things I think that sort of came out of it. Number one is like it's easy to think of Colton as okay, I made a little language that now has static types and it's kind of like Common Lisp, but we have to, go through this extra ceremony of working with types. I don't see it like that at all. Yes, there is extra ceremony. Yes, there are types. All that stuff is true. But types themselves also give you programming language abstractions that you cannot have if you don't have the types. The easiest example, I think, of this, the simplest example, is that I frequently mention this, is the fact that you can have code that effectively dispatches on its return type. So, for example, maybe I want to do a data type conversion. I have a some input type and I want to convert it to some output type.
Mm.
But I don't, I'm writing all this high level polymorphic code. I don't know what output type I want to convert it to because there's not enough constraints present in my program to ascertain that yet. In Lisp, you effectively can't sort of do this. You can't change the output type of a function. Or sorry, you can't change the function itself depending on its output type. I mean, how is it possible to do that? Like if I have a function that let's suppose a function always takes an integer as input.
Mm.
And depending on the context, the output will be a floating point number, maybe a string, maybe whatever. If I'm concatenating this thing with a string, then I should know I should be converting this integer to a string. If I'm doing double float arithmetic, maybe I need to know that I can convert this thing to a double float. The context is what determines that. How would I do this in Lisp? Lisp, being a dynamic language, I can send the integer into this function. How does that function know, quote unquote, that it should be returning a string or it
Yeah,
should
it
be
can't, right?
returning a double float? It can't. So the Lisp, in Common Lisp, there are a couple functions that are like this. Common Lisp has a function called coerce. Common Lisp also has a function called concatenate, which concatenates sequences. But in both of these cases, you have to supply the output type as an argument to the function itself. So you say concatenate space string space your arguments to say concatenate all these things together, but make sure it outputs a string.
Mm.
Concatenate list. Concatenate all these things together, but make sure it outputs a list. Same thing with coerce. Coerce some object, single float or double float or whatever. So you have to be explicit on that input type. When you have a type system like of the style of standard ML or Haskell, your types are all statically determined, and so you literally infer from context that this thing should return a string. So the function we should call is the string version of this function. This is a fundamentally new facility in your programming language that you do not get in a dynamically typed language. And there are, of course, other examples as well. So we get these facilities that we wouldn't otherwise get. Is one thing. The second part is that structuring large programs, now you have some, I don't know what you'd call it, not guardrails, but like if I'm working on a team with 10 people and we're all writing code,
Mm.
what is the best way for us to communicate with each other about what the code we're writing does, what the interface is, how you call each other's functions, how you construct each other's data types, and so on. How do we do this? Well, in Common Lisp, if you're writing Common Lisp professionally, what you're going to do is you're going to define your package or namespace, whatever you want to call it. In Lisp, it's called a package. You write your functions. You be meticulous about writing doc strings for every
Mm.
function. In the doc string, you be meticulous about saying this argument type X has this argument X has type integer, this argument whatever, and maybe you give a couple examples if you're being very rigorous. And a lot of professional programming is not always so rigorous. And then you go to your teammates and say, "Hey, go read my source code. Here's the package. Here are all the functions." Just kind of look at the documentation. With Colton, like you would get with any other language like Haskell or OCaml or whatever, you define your code, and already the like type system is providing a form of documentation. It's providing a form of double checking that you're using the code that was written adequately, and so on and so forth. So, I mean, I think, again, to all listeners of this podcast, everybody recognizes the value of having types, and Colton sort of brings that benefit to Lisp so long as you decide to use Colton for these things.
Mm.
Um, so it ends up affecting kind of what development style is actually possible on a professional team, I think, if you use these things. Now again, everything that I said before is still true. Maybe you still do write a good chunk of Common Lisp code, but maybe it's not as important that that is so correct or so optimized or so whatever. Um, and you still get by with that. So it's not sort of an all or nothing thing, I think. You're able as a programmer or software engineer to kind of strike the balance that's appropriate for what's being worked on.
Mm. Yeah, because when, like you said, I think there are at least well, many of our listeners are like on board with the like whole benefits of static typing. But I think the ones who object against static typing usually say that, well, it comes at the cost of like expressivity, or uh, letting me like I don't know, leverage these dynamic features. But it sounds from what you're saying that you can sort of find a compromise, just like or maybe compromise is the wrong word actually. Like you can sort of have it both ways if you want, with like Colton, for example.
Yeah, it's not, I wouldn't say that everything is like, it doesn't make using Colton and Common Lisp doesn't automatically mean that you now have like the freewheeling ability to be dynamic and static however and wherever you want. There's still some rigor and still some like proper engineering analysis to do where you kind of want to draw that line. But again, the ethos of Common Lisp, in my view, is that the programmer is ultimately the person who should be making these decisions. The tooling should not be imposing these decisions on you in a way where you have no choice to make this trade-off. You see this, I think, even in a lot of static type systems like Haskell, for example. Haskell, of course, is very renowned for being extraordinarily rigid in how you can write programs. I mean, it's not just the type system, it's also the purity constraint, it's
Mm.
also the laziness and whatever. It's very, generally speaking, it's very rigid in what it allows as a valid program. But even in a language like Haskell, eventually, if you put something to use long enough, people will want ways of circumventing the facilities that are imposed by the tool. And so Haskell, of course, again, famously has many operators in the language. The most popular of which is like unsafe perform IO
Mm.
to let you kind of get around something.
Yeah,
And
trust me.
I
Like,
think, yeah, right, exactly. And so I think that the dynamic language people that argue against static types do have a point to an extent that, like, how do I want to word this? It seems in practice, so if I look empirically at the systems that have been built, almost always asymptotically, there will be some way to get around the constraints of the system because a programmer will eventually want those things.
mm.
I think in a language like Haskell, the surface area for allowing this is very small. There are very few functions that exist that allow you to kind of skirt it. I think Colton is an example of a system that is much more. Um, it allows you to dial that the way you want a little bit more easily. It's not that you have an extremely, let's call it, dogmatic core with a couple little escape hatches. It's more you can take a step back and design your program. Which part of your program do you really want to be static, take advantage of the facilities that static typing brings you? In what part of your program do you want to be dynamic and take advantage of the dynamic features? And have a very well defined interface between those things that doesn't incur any or minimal performance penalty between them. I personally see merit in sort of both ways of thinking, which is why I want both for my
Mm.
programs.
Yeah, you
And I
want the
think
like
in
freedom
practice
to
it works quite
choose.
well. Yeah, exactly. Freedom to choose and freedom to kind of, again, it's not so simple. It's not easy to just think of it as a percentage. Like you don't upfront say, okay, I'm going to write 10% of my program in Common Lisp and 90% in Colton. It's not so delineated. But the fact of the matter is, especially if you kind of think of your program in terms of modules on a per module basis, you can sort of answer the question, is it important for me to take advantage of the facilities offered by static types?
Mm,
Maybe that decision is driven by performance. Um, I don't know. I haven't written a great deal of like high performance closure code in a while, but like one of my consternations with writing closure is within the closure language itself, I feel like I don't really get to decide that so often. I feel like I have to buy into the sort of closure philosophy of immutable data structures and I don't know transducers and the closure sort of way of thinking. It's not that I start a closure module and think, okay, what how do I want to shape this module to best satisfy the requirements of my program?
mm,
I would claim that at least in the domains that I work in, the combination of Common Lisp and Colton gives me a better ability to choose these things.
mm,
Maybe if I want for this particular module absolute safety, because this module is mission critical, it can't fail, or maybe I want as fast speed as possible, or maybe I want to be able to build a module where I can extend the protocol of something. In the former two cases, I would want to use Colton. In the latter, I would want to use Common Lisp. And as long as they can talk to each other, there's no problem. And I think that's kind of what you get out of it. It's hard for me to see an argument against that. Like, why wouldn't you want to be able to choose?
mm.
Um, I mean, some people might say, well, now if you have a choice, now and you're running a large team, well, then now you have half the team choosing one way, half the team choosing another way. I suppose that's an argument. But again, in the types of software that I write professionally, being able to make these decisions, I think, is crucial.
Mm. Yeah, I guess it's like there's always this like just this is tension as well. I guess like freedom versus like predictability versus expressivity or whatever. Like some
Hmm.
people like to drive stick. Some people always want like automatic. The and I guess there's like well positives for both approaches. But I mean, it sounds like, I mean, the way when you talk about Common Lisp, it's sort of like, I don't know, feels like there's some sort of like this very Lispy philosophy, like if we circle back to like the way the Lisp machines, etc., were marketed, is that you are sort of uh, the user is the programmer is the user, and like vice versa. Like the Common Lisp can act as a substrate, for example, to like build pretty much anything you want. You can sort of shape it. For, I mean, going back to the closure example, I think Rich Hickey, when he designed it, he had a very particular use case in mind, and like I want to ship this, and I want to maximize like closure for this like particular situation, like for example JVM interop and like focusing on like data transformations, etc. But yeah, then of course that comes with the trade-off, is that that it is what it is. What you see is what you get, pretty much. Like there's not that much uh, room for, I don't know, like tweaking and making it yeah, like adapting the tool for the job, so to speak.
Yeah, this ultimately circles back to the whole like discussion of what the merit of a DSL is. So the idea of a DSL is that you can express whatever thing you need to express in the specific domain of interest in a clear, concise, efficient, succinct way. It's the reason we have a DSL, is so that we can do that sort of thing without having to also buy into the ceremony of the rest of programming. Like we can focus on the DSL in a sort of well delineated portion of our program, right in that DSL, and the rest of our program is just sort of ordinary. In a way, this kind of discussion of flexibility, dichotomy between static, dynamic, whatever, is in a way can be kind of rewound and viewed in this lens of the DSL. Colton maybe shouldn't be seen as like an alternative to Common Lisp. Maybe it should be, it's best seen as like a DSL within Lisp, not unlike the loop facility in Lisp. So for background, the loop facility in Lisp is this other DSL that's built into Lisp for writing loops. And it's amazingly baroque. Like you can do a lot of things with it. It's like this. It almost looks like reading Pascal or something when you
Mm.
write a loop macro in Lisp. But in some cases, if you're doing some complicated loop, at least in my experience, it's like totally reasonable. It's clear. It expresses the idea I want very simply, whatever. And so the idea that a DSL exists is for the benefit for the user to choose that that is something that will effectively express the program they want to express. Colton, in that way, is like that. Like you said, Lisp, the ethos of Lisp is everything's accessible to you. You can sort of do anything. To put it in very simple terms,
Mm.
you can write in whatever paradigm you want. You can write assembly code in Lisp. You can write functional programs in Lisp. You can runtime debug. You can just do a lot of stuff. You can build macros to express. You can do everything at everything, quote unquote. Um, Colton is a DSL, a very sophisticated and large DSL, but nonetheless a DSL, and it presents an opportunity to express parts of your program that benefit from it, not unlike parts of your program that benefit from loops. It
Mm.
just happens that the surface area of the Colton DSL is much larger than like a loop DSL, I think. Now, it could have been that I threw my hands in the air and said, you know what, Common Lisp, screw this. I can't write my efficient programs nicely. I'm going to pull a Rich Hickey and I'm going to go build an entire new language called Colton. It's going to have its separate compiler. It's going to run on, I don't know, .NET or something.
Mm.
It's going to have static types. It's going to do all these things. I'm going to reinvent the entire ecosystem with my dogmatic view for how programs should be built to satisfy whatever domain requirements that I'm interested in. I could have done that, but if I do that, I'm robbing myself of the opportunity to make these trade-offs that I discussed earlier. If I do that, I now no longer can decide I want this part of my program to be this, and I want this part of my program to be this, or right now I really care about performance, and over here I don't care about performance. I've now built an entire system founded on sort of a single core collection of principles, and now I kind of must sleep in the bed I made, so to speak. And I feel
Mm.
that a little bit with Clojure. I think Clojure, by the way, is a very well designed language. I think Rich and team have done an amazing job. So this isn't an indictment against Clojure, to be clear. I don't think it was unreasonable to build what he built. I'm just saying that, um, at least as far as what I wanted, I had something that I was not happy about in the tooling that I had. I understood that Common Lisp, in theory, gave me the ability to solve this problem, but it just would take a lot of work to do it. And in lieu of just saying, well, screw all of Common Lisp, let me try to improve Common Lisp by offering this. A similar language that really tries to promote this, I think, is Racket. Racket is leaps and bounds better than Common Lisp at making DSLs. They have very, very good facilities for building DSLs in a very principled manner, I guess I would say, in a very
Mm.
organized and principled manner. And that could have been another option that I did. Instead of building this in Common Lisp, I could have built it in Racket. There's an interesting project called Hackett by Alexis King that builds literally Haskell a very small derivative of Haskell into Racket. And it's sort of the premise is somewhat similar to that of Colton, where you can kind of use Racket for whatever you want here, and Colton for, or sorry, not Colton, Hackett for whatever you want over here, and all the programs can be side by side
Mm.
and intermingle and so on. So I could have done that in principle, but I just found Common Lisp is the one that has more industry adoption. It has a lot of these, for lack of a better term, pragmatic features kind of built in. It's a standardized language. There are a lot of compilers for it and so on. And I think that that made sense to me for Colton.
Yeah.
Um, so yeah, I think this interesting view of instead of embarking on building an entirely new language, to do so as an extension to a language that exists, for better or for worse, Lisp-like languages are some of the only languages that really make it feasible to do something like that.
Mm.
You couldn't really do that in C. I don't know if you've ever seen uh, these macro monstrosities written in C to allow kind of a separate style of programming.
Yeah, no, no, yeah. You don't want to do that.
Yeah, right. That's right.
Yeah. And like and it looks from what I can see that it has paid off because you're actually using Colton in production, right? Like at your regular day job, if I'm not mistaken.
Yeah, that's right. So Colton started as Colton started as a weekend project for all the reasons that I said earlier. The first time it really kind of saw light as something that could actually be valuable for the use at a company was when I was working in quantum computing. So I've been working in quantum computing and doing quantum compiler implementation stuff, quantum programming language stuff, which is a whole separate ball game from all this ordinary classical programming. And I was working in that for about 10 years. And quantum compilers are really, really hard to write. They're nothing like normal compilers. They have a
I'm
lot of
not
math in
surprised.
them. Yeah, there's a lot of math involved in them. You're manipulating all these crazy data, like these matrices over the ring of the field extension of the complex numbers, or not complex numbers, like integers with a field extension of some root of unity or something, or ring extension rather. All these crazy math data types and whatever, and it's like there's a compiler written in Common Lisp called Quil-C. Quil is the name of a quantum programming language. Quil-C is the compiler, and like similar to what I said before, it sort of reached a point where it's difficult to express certain programs and certain quantum compiler optimizations in Quil-C in Common Lisp. Again, we could solve this by more macros or more this, but like this was a case where we really wish we could have just written it in this portion in Haskell or something.
Mm.
So it's like at work, it's like, well, we could just use Colton for this now. And then there was the usual debate, like, are we sure? Because Colton isn't really mature. Should we really be building production code on this? And what we ended up doing is saying, okay, we can use Colton, but here's the list of things that the language would need to satisfy to justify it being used in sort of a production environment. And so, long story short, Colton was ended up being used for implementing this quantum compiler stuff. It implements two major modules of the Quil-C compiler, which is open source, so it's viewable, accessible online. One of these is this very number theoretic way of compiling a quantum program into sort of a discrete instruction set. And then the other is this quantum program super optimizer. Both of these are state-of-the-art techniques described in like the latest research papers, and Colton was phenomenal. Actually, the super interesting thing about both of them is both of these programs were written by people who have never had Lisp experience before. They had never written a single line of Common Lisp. They just went straight into Colton and
Okay.
wrote it in Colton. And it was hugely successful. From their own testimonies, it's like, now if I'm calling a function wrong, at least the compiler can warn me. I don't have to like run the
Mm.
program to see that I get a type error or whatever. And moreover, and more subtle than that, when they're building this big complicated extension to the program, the types are sort of reinforcing their own thinking, if that makes sense. Like they're already unfamiliar with the language and Lisp and all this, Emacs stuff and whatever.
Mm.
But the fact that, they're writing this program which is thousands of lines long, uh, the types that they write are helping them understand the
Mm.
thing that they had already written. It sort of helps it keep it in their mind and so on. So those were the two first big use cases in quantum computing. And then I've taken a hiatus from quantum computing. I'll probably return someday to it, but like 10 years was enough for me to back up for a little while from it. And now sort of in my day job now, which is working at this stealth startup doing sort of defense related stuff. It's like absolutely instrumental. It's so beneficial what we get out of it because a lot of it is like signal processing stuff. There's a lot of like when you're doing signal processing, most of the time it has to be quasi real time. You can't spend time doing stuff that isn't like transforming numbers around, basically. You cannot be goofing around allocating a bunch of objects in memory and chasing
Mm.
pointers around. It has to be like really pipelined, efficient code. But when you read the code, it just reads like normal. It's just like regular code. It's not this like beaten into a pulp stuff because the Colton optimizer is doing monomorphization and inlining and specialization and representation selection and you know using efficient representations of data types and all of that. And the code just reads mostly normal. And it's developed interactively, like a normal Lisp program. And the rest of the program, which isn't Colton, it's just Common Lisp. I don't know. There's this good what's the good management word for this synergy between it all that
Mm.
I think works really really well in sort of a professional environment. You know, I'm describing this as being all peaches and cream, but the fact of the matter is too that Colton is not like what I would consider to be a 1.0 product. It is not unheard of at my job that it's like actually a specific example of a deficiency was like who doesn't love the maybe or optional type,
Mm.
right? This is like one of the first things that you learn about in functional programming is the maybe or optional type or option type, whatever you want to
Yeah. Yeah.
call it. It's like we don't have null pointers in our language because we can always check whether something is valid or not valid, and we use the maybe type. Of course, we have that in Colton, no
Mm.
questions about that. But like, and it's used quite pervasively in the standard library, as is normal. But like we're writing the signal processing code, and it's like one of the functions in the pipeline uses maybe, or as it's called in Colton, optional, and it's returning, in Colton it's called sum and none. So sum of x and none. And somewhere it's returning, sum of, some floating point number or something like that. And what does that mean? Okay, so the compiler is going to allocate this thing, or it's going to emit code that allocates a box to the heap, which is the sum value, and that sum value is going to have a pointer to the floating point value underneath it. And
Mm.
it's like again, and this is like in some inner loop that's like being calculated a billion times or whatever. It's like you can't have that there and
No.
this is one of these examples where it's like, okay, if I'm using like, if I'm using another language where this is just a built, baked-in thing, well, my only option is to like re-architect my code and functions to not use it somehow, which maybe means reinventing standard library functions. In Colton, it's like, well, we can also just modify the compiler too if we want. So
Yeah.
I go read about the state of the art of this stuff. I'm like, what does OCaml do? Like OCaml is a very respected language. It's used at Jane Street. It's optimized. It's like a very and it's been around for forever. It's a good language. And I go read about it and it's like, oh, okay, they also allocate optionals
Yeah.
or options as they're called. They still allocate something to the heap every time. It's
And
like,
the
yeah, go
catch
ahead.
is that you can't, like, you can't, I mean, since it has to track that it's actually some case of this like tagged union, it can't
Yes.
just like put, I don't know, it can't just put like a value on the stack. It has to actually be like either have some like it has to have some kind of like runtime type
Yes,
information.
exactly. It's something has to be there. Now, if I went to one of my team meetings with the old signal processing graybeards. I'm like, oh, by the way, I can't get the signal processing code to work because I'm forced to allocate this box representation. They're gonna be like, what the F are you talking about? Like, just go rewrite it in C or something and just use a null pointer or something like that has no runtime cost. I mean, I think a lot of people who are not functional programmers sometimes view the issues of functional programming as truly having simple solutions like that.
Mm.
And in a way, they're right. If we only look at the problem from this very narrow lens, it's true. A null pointer would be perfectly sufficient. Now, of course, when we zoom out and look at the programming in the large and error checking and blah, 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 we know that there are arguments against it. But nonetheless, this is an example of something where we were blocked on making progress on something because of inefficiency due to a very normal, very standard feature of functional programming. So what we looked at, there's some paper from a workshop like 2 years ago on how to stop making optionals allocate in OCaml, and there's this gargantuan module system thing, and you had to modify the compiler, the module. I don't remember all the details, but it's like this thing. I'm like my face is like going flush because I'm like this is not. There has to be something better than this. So anyway, we worked on this a little bit, and it turns out there's a little neat trick you can do if you are able to modify your representation of data types, which we can because Colton is not some 1.0 product yet. And we made it so optionals just don't allocate. And what it does is it creates roughly speaking, it creates like a distinguished symbol that's not accessible to the programmer. And whenever none is represented, it uses that symbol kind of like a null pointer internally. And when you have sum, the sum function acts as identity for all of your values that you supply to it, except for one.
Mm.
There's only one value for which sum does allocation, which is when you do sum of none. If you can distinguish none, sum of none, sum of none, sum to the power of n of none, if you can distinguish those cases, you can make it so that optional does not allocate. You only need to distinguish that at runtime. So when you're checking if something is sum, you have to check only if it's a sum of none sort of thing.
Mm.
It makes sense if we pulled
Yeah.
up the code and looked at it and whatever, our assistant should be pulling up the implementation in Colton right now or whatever, show it on the screen. But
Yeah.
anyway, the
Jamie,
point
pull
is,
that up.
yeah, yeah, right.
Yeah, no,
But the
but
point
I get it
is,
because like you sort of like that's the one case you need to be able to distinguish. Like was there because that's that classic thing where like well in Lisp for example, in some Lisps when you try to access an object in a map, for example, you return nil, and like
correct, yeah,
you have to be able to distinguish like you want to be able to distinguish like did I actually put the nil there in the map like
correct,
intentionally,
correct.
or did I just like hit the missing key? And like if you make a distinguish between those cases, then like okay, then you can tell them apart.
Yeah, and the type system in this case, the type system encodes how nested the optional is. Now, it's not very frequent that you have much nesting of optionals. It's, usually it's just sum of a data type T or none. Usually you don't have option of option of option of option of option of whatever. So,
Yeah, then
but
you have other
nonetheless,
problems.
yeah, yeah, right. But nonetheless, we like modified the Colton compiler, and so now sum does not allocate except in one case, which is if you do sum of sum of sum of sum of none,
Okay.
or any greater number. If you do that, then it will allocate a value at runtime. If you do sum of none, or just sum of none, or sum of five, or sum of 100, it doesn't allocate anything. And so now we can design all of our APIs to use optionals at no memory cost. Now,
Mm.
there is a small performance penalty, which is we have to check at runtime when we're dispatching within the union whether something is sum or none. So we have to do some equality check at some point, but that's the only cost is basically a pointer equality. And so we implemented this in Colton. And again, I just maybe going back to some of my piquant opinions or whatever,
Mm.
why are other languages not doing this? or why, really in particular, why does OCaml not do this? I'm sure they have a good reason, and I don't care to go investigate or whatever. But I think when you look at functional programming language adoption, not that functional programming language adoption is all hinged on this one, you know, design decision about how to work with optionals. Of course not. It's much more complicated. But I think this is an example where when you talk to C++ programmers or Rust programmers or whatever, these are the kinds of things they're talking about where there are like inefficiencies that they're just not used to having in their ordinary code development paths. And a lot of the work of Colton is not to just keep dialing up safety and safety and safety. As I think you know from the talk I gave, I have some opinions on advertising safety in programming languages and whatever. I think
Mm.
a lot of these people really want to see that um, abstractions aren't costing them, ideally, that it's costing them nothing, but
Yeah, like the
slightly less ideally, it
Rust
doesn't cost them too
tagline.
much.
Yeah.
Yeah, exactly, exactly. Rust, by the way, is also a language that if you go look at the rules of their option type, it's kind of complicated because they can give you pointers and you can do a lot of stuff in Rust. But in most ordinary cases, they also don't have to allocate. The representation of a data type T is equivalent to an option of T modulo some set of, uh, caveats, constraints, or
Mm.
whatever. So, as the story ends with this, as we implement this feature, we now get the benefit of that functional programming aspect, and the code is efficient while not sort of giving up things. And so, a lot of the sort of Colton effort, I would say, is really pushing boundaries of what we can optimize in the language, which we get a lot better when we have a full type system a la Haskell's, when we have a very good optimizing compiler like SBCL, the underlying Lisp compiler,
Mm.
and when we have some control uh, over the compilation process of Colton to Lisp. Which, as a side note, the Colton compiler is, I'm not going to say it's the best compiler. Maybe I should, as just to be proud of myself. But the people who work on the Colton compiler are people who have like no compiler experience. Again, I don't know if you've ever looked at LLVM, like opened up the LLVM code or ever imagined like making a change to LLVM. It is so complicated. To build LLVM is even complicated. Because Colton already relies on the Lisp compiler to do all the dirty work of like producing assembly code and all of that stuff. Colton is able to focus on the parts of the compiler that matter, if that makes sense. The
Mm.
parts of the compiler that do code transformations and type checking and so on, kind of the meat of what a compiler uh, should do.
Yeah, it's a
Maybe that's
horizontal slice of the, like, because usually compilers like really really deep, like lots of different passes, but you sort of
correct.
have to focus on the most interesting part, I guess.
Yeah, yeah, maybe that's the best way. It's not really the meat, it's just the interesting part. I mean, some people find code gen very interesting, and some people
Mm.
find parsing very interesting. Most people who get into compilers really like the optimization and the sort of IR transformation stuff to be kind of the most interesting. And the nice thing about Colton is it can really just focus its abstractions on just that. And so what that means is the compiler is relatively accessible for hacking. It could be better. There's some stuff that's not very well documented. Usual caveats apply with a project that is constantly evolving.
Mm.
But like a lot of the optimizations that are included in Colton uh, are done by people who have never touched a compiler. Like the heuristic, Colton has a heuristic inliner. It will look at code. It will like look at some properties of the code and make a decision. Should I inline this or should I not? That's something that doesn't exist at all in Lisp and cannot really exist in Lisp, by the way.
Yeah,
It's built
yeah.
in Colton, and this was built as a open source contribution by somebody who doesn't write compilers. Like, I can't imagine myself as a person who's like, neck deep in quantum compilers, classical compilers, going to LLVM and building like a speculative or not speculative heuristic inliner. I mean, maybe if I spend, I don't know, a year on it or something, maybe I could,
Mm.
crack that. But just having a drive by anyway, I'm rambling now, but I think that is it's a very fun part of programming language development when the compiler is something that's actually reasonably accessible, I think.
Mm,
And it's proven to be valuable for like optimizing this option type thing, for adding new passes to the compiler to optimize further, and so on and so forth.
yeah. Yeah, I don't know. It sounds really exciting, and this is sort of like a pet theory that I've had for a while. That I think we're gonna see more. Like if there, I don't know, who knows what's gonna happen with AI and stuff. People sort of start calling the end of history of programming already. Like I'm not so certain about that, but I've had this feeling for quite a while that probably like the next generation of programming languages, if we ever see one, is probably going to be like not like you said, like not like you said, like you go on and you're not happy with how the programming language looks, so you go away and write your whole like new runtime, new language, everything from scratch. Feels like probably the next generation of programming languages, I think at least, are gonna be more in the line with Colton. Like you have an existing system or an existing platform, and then you sort of write something that can live inside of that to sort of like, I don't know, reach new abstraction level or do something that wouldn't be like practical before.
Yeah,
Uh,
I think that there's like historically, well, I'm not the one to ask about all the history of like compiler software architectures or whatever, but like LLVM was one such, uh, would you call it a breakthrough? I don't know if it's a breakthrough, but the idea that the compiler toolkit, and I know there were some C compiler toolkits before that as well, but like the Tendra C compiler, I think is like a toolkit. There's a few others. The portable C compiler, I think, was another.
mm,
I'm not up to date on all the history and latest of compiler toolkits, but the idea that like yes, a lot of the parts of a compiler shouldn't have to be rewritten from scratch every single time. We shouldn't have to rewrite a freaking garbage collector every time we build a new language. It's like a complicated thing, and the garbage collector is always super difficult to write and to make it really good, that is. And, we shouldn't have to redo all of this stuff. And I think so, like projects like LLVM really brought to the spotlight that we could have a platform for building compilers on top of which we could build our own little code generators. As long as we got into LLVM IR, the rest would sort of be taken care of. um, that's kind of how I started cutting my teeth into compilers forever ago, was building on top of LLVM. It was painstaking, annoying. LLVM would update and all your code would break, and it was super aggravating. But it was like it did relieve the burden of like having to read a book about x86 assembly code. I mean, really, really understanding x86 assembly code. I'm not talking about like, I know that the add instruction adds, and I know that the mul
mm,
instruction multiply. I'm talking about the really low level details of like cycle counts, instruction like resource dependencies, and how to break those dependencies. How to really make a true, honest code gen pass of a compiler requires really deep, intimate knowledge if you want to make it good, that is. And LLVM is an example of a project that sort of alleviated that need. Now, I think you're right that we will continue to go in that direction, but I will say one thing. I think that languages like Zig and others have demonstrated that there's still a lot of value to be had in having very good UX.
mm. Yeah, yeah.
Zig, again, I'm not intimately familiar with the language or tool chain, but it's an example where like being able to cross compile anything, like it came to a point where a lot of people were cross compiling C code using the Zig tool chain rather than their native C tool chain, because GCC, it's like whatever super inscrutable, I don't know, whatever you have to write at the command line to compile for different architectures, like 20 options. You have to command the linker to do something. You have to have a distribution of your shared live. It's like super complicated. And Zig made it very, very simple. It's like, one little short command to cross compile a C program, ignore Zig, a C program to a different architecture. And I think people, I don't want to speak for Andrew Kelly, the creator of Zig,
Mm,
but I think people like him sometimes feel that the only way they can realize their vision for how something ought to work is to build it from scratch. And so I do think that there will be that people will continue to sort of build things from scratch because they feel that that gives them the most control to realize something from a UX perspective or functionality perspective or so on. I hope that we don't have to continue doing that. I have this, probably um, unrealistic dream that we can still like share code with one another and we can build
Mm.
off each other's work so that like humanity, like in the same way that mathematics and physics and whatever build on the shoulders of the giants before them or whatever, we could sort of have the same effect with software. I don't think we're quite there yet. There's a lot of unsolved problems and code reuse and so on. But as it pertains to compilers, all I can say is that an architecture like Colton, relying on an existing compiler to do a lot of the stuff that I shouldn't have to care about, has been really, really refreshing and really, really nice for the development providers. And I hope other people take that model for things with Lisp
Mm.
or with other technologies.
Yeah, and it, I mean that's exactly it, right? Like if you do that, you can sort of stand on the shoulder of giants. And I was thinking about that thing you said at work as well, when you had to sort of sell Colton to like the rest of the organization. I mean, it's a much lower risk thing, right? Like when you can say like, well, basically all it is another macro, right? It's a library and a
Yes. Yeah.
macro. I mean, and then like it's not like you don't have to throw all of your Common Lisp code away. You can just like add this thing on top, and it
Yeah.
interoperates with the rest of the system.
Yeah. And kind of like you were indexing on initially, if I was proposing that we were using a completely new compile, even if it had perfect Lisp interop, but it was a separate system, if I was going to realistically pitch like we have our own like x86 backend, ARM backend. All the assembly code is manually written. We have our own dynamic language runtime with a garbage collector and all of that. And we now have to sort of care about all of that in a sort of first party manner. It's too complicated. It's not going to fly. I mean, most companies where you're going to be doing stuff like this, short of working at a Google where you have, I don't know, infinite money or something like that, you really have to pick and choose your battles.
Mm.
And you can't, hire a team of 50, you know, 20% of which are going to work on the garbage collector or something like that. So being able to say, look, like you said, this really is just a macro. It is already it produces code which is already compatible with our stuff. Nothing about the tool chain changes. Lisp uses a build system called ASDF, which stands for Another System Definition Facility.
Yeah.
There's no like, there's no there's no additions to that. Everything just sort of slots in to the existing things, and I think that's what makes it in large part a feasible technology to use. I think the costs of changing tool chains again should never be understated. If I want to change a tool chain or add a language to a company or something, and if you're a professional software engineering shop, you have to go through all this work. You have to make it work with, like, we didn't have to do anything for CI/CD. I know it sounds really stupid, and I know it sounds very like boring. Nobody wants to think about building CI/CD systems or something when they want to do the cool programming or they're calculating cool signal processing stuff.
Mm.
But it's just a non-problem if what you're building is already a part of like an existing piece of infrastructure. So CI/CD, we just write unit tests as normal, and it gets run normal. So adopting Colton for us in our organization was literally just adding one line dependency to our build system to say, now you depend on Colton. That's it. That's all you need. And then, of course, you have to write code and actually do your job. But there's no other like cost to buy into that. And I don't feel like I see enough of that. I feel like a lot of pitches for programming languages are sort of, you have to do everything from scratch
Mm.
again. If I want to adopt, I don't know, um, like there's a programming language called Jank, which is like a closure, like kind of like a native
Mm.
closure
Compiled.
dialect. So
Yeah.
yeah, compiled native Clojure dialect, it's like that's not going to just fit into my Clojure ecosystem. I'm going to have to figure out how to invoke this compiler from my CI/CD system, how to install the compiler onto the CI/CD system, how to run my unit test, how to do that, how to do that. Again, not an indictment on that language in particular, just using it as an example. Um, but it's like a lot of work if you want to productionize its use as a serious thing in an organization. And a lot of organizations just don't want to pay the cost of doing that, the
Mm.
human time cost and the literal money of paying people cost to do that. People want to focus on the products they're building, not all of this. And so again, the organization I joined was already using Common Lisp. Using Colton as a part of that is just like a discussion that is not unlike just adding another dependency to the project. It's like, can we use this to write some stuff? Everybody's like, yeah, sure, let's do it.
Mm.
If it doesn't work, we can just delete it. We can just
Mm.
remove the line of dependency. It doesn't cost anything. So I think that's another one of these unintended. I didn't think about that at all when I was first authoring Colton. I didn't even think about professional use of it. But it's like another one of these nice benefits by piggybacking off of an existing ecosystem, I think.
Mm. Yeah, and I mean Clojure, like you mentioned, is built on top of the JVM. I mean that was no accident either. It's like it sort of can sort of I don't know, make adoption easier and make it easier to sell to management. Like it's just uh, don't need to throw away all of your like build systems and infrastructure, etc. Like as long as if you can build Java, you can build Clojure pretty much.
Yeah, exactly. And I think that has been a major source of success for the language is that it's not difficult to adopt, and perhaps more importantly, it's not difficult to eject if it's
Mm.
not working well. It's very easy and cheap to try it. Presuming you're already a JVM shop, of course, it's very easy and cheap to try it, and you're not like investing too much compared to like using Haskell. If I were to like previous jobs, for example, go to my boss and say, let's use Haskell, uh, then the natural question is going to, I mean, there's going to be a million questions. If they don't just say no out of the gate, it's going to be like, well, how do we integrate this? All the tools we're using for profiling, what are we going to use there? All the tools for, I don't know, code coverage, what are we going to use there? How do we run unit tests? What are you going to agree on? It's just a lot of work to bring that stuff in, and it's nice if you don't have it's just a no-brainer to use something because you already use a set of technologies, I
Mm.
think.
Yeah, yeah, yeah. Like I said before, it's there's a dawn of a new age with AI, etc. So like who knows? But I don't know. Hopefully we can like keep just try to build more on existing infrastructure instead of like trying to reinvent the wheel all the time.
Yeah,
Yeah, we're running out of time, I think. But yeah, I just want to ask Robert, like, where can people find you, and where can they find out more about Colton?
yeah, sure. Probably the easiest if you're into Twitter or X, the Everything app. I post a lot as Style Warning there. I also have a website, stylewarning.com, where I occasionally write little blog posts and stuff like that. Colton is also easy to find on the internet, colton-lang.github.io. Or if you search Colton on Google, Coalton, you're either going to get some city in Ohio that used to be a coal town, or you'll get this functional programming language. From there, you can find folks on Discord and whatever. What I can say is that uh, i if people are interested in kind of trying their hand at language development or language experimentation, or they want to take part in building up a programming language without having to sort of commit themselves to it fully, I think Colton is like a great place to start. There's a lot of nice kind of starter issues. There's a good team on the Discord who will help kind of point you to the right place in the code to do something. It's like a nice starter language development pathway, in my opinion. without having to really buy into, the commitment of doing it very long term. And it's something that's actually used in real life. So you can find both of those things, and you can find me and that kind of in both those places.
Nice, very cool. Just one question that occurred to me just now. Like,
Yeah.
where does the name Colton come from?
Oh, this is very this is a mixture of like a bunch of different things. So the first is that there's a compiler called that I mentioned earlier called Milton,
Yeah,
and it's
Milton.
spelled Mlton. And I'm like, I want to make a Lisp version of that, so I'm going to call it Clton. But then I was thinking like, okay, when I'm like speaking to somebody like you about this project, I'm going to be like, it's Colton, or I'm going to pronounce it, or I'm going to call it Clton, or maybe, or Colton, like you pronounce Milton.
Mm.
But then I'm going to be like, but actually, just know that it's CL, not COAL, whatever. So I'm like, okay, I'm going to call it Col. Well, why Col? Because the most popular Lisp compiler is called SVCL, Steel Bank Common Lisp. Steel and Bank being associated with Carnegie and Mellon of
Mm.
Carnegie Mellon Common Lisp, which was a Common Lisp compiler that came from before. And I'm like, what's a raw material that's like kind of like steel? And I'm like, okay, coal.
Yeah.
I don't know. So it's like, I
Yeah,
don't know,
fair
it's like
enough.
a triple entendre, I guess. That's what the
Yeah,
name
yeah,
came
yeah,
from.
yeah, yeah. I mean,
Yeah.
uh, I think as long as it's easy to say and it's easy to Google, I think it's like that's a really good like starting point for
Yes, yeah,
naming
like I
something.
said, there's not a lot of it's hard to confuse it. There's not other technologies. It's either, some low population town in the middle of, industrial America, or it's this, strange common Lisp project. So it's very easy to find.
Mm, mm. Yeah, and it doesn't start with V either. I heard from in a previous episode that like apparently that end of the alphabet is like very very densely populated like language.
Yeah, yeah, right.
Uh,
Yeah, I mean, we could have a whole nother discussion about like naming of things and like how to best advertise your product. If you choose a strange name of something, then you always have to append something like Lang to it, like
mm,
Janet Lang, or something
Golang.
like that, or Go Lang. Yeah, Go Lang is even better of an example. So, and then it like canonically becomes that name. Like, of course, people still say Go, but it's like almost canonically like, hey, I write in Golang now. Sort of morphed a little bit.
Yeah,
But
yeah.
yeah, it's nice to choose a name that's like easy to say, easy to Google, isn't too crowded in terms of other similarly named things and so on. I think
Mm.
Colton fits that bill reasonably well.
Yep, yep, yeah, yeah. Okay, but yes, people know where to find you now, and yeah, I just want to give you a huge thank you, Robert, for coming on the
Yeah,
podcast and
yeah. Thanks a
sharing.
lot. I'm happy to, very happy to have shared kind of a little bit of a different view of kind of the functional programming language universe. I think Lisp and Colton, of course, are very kind of unique in how they're situated in the larger ethos of functional programming. And I'm very happy to finally get to be able to talk about this.
Mm. Yes. Yeah, I hope our listeners enjoyed it as much as I did. Yes. Well, I'll catch you later, Robert.
Yeah, thanks a lot.
Yeah,
I'll
have a
catch
nice
you
day.
later. Yeah, you too.